Have you ever just stopped and wondered how anything works? I mean, really works. We're about to pull back the curtain on the invisible, unbreakable rules that govern how our entire world transforms. We're talking about the absolute fundamentals of chemistry.
I mean, just look around you. You see a log burning in a fireplace turning into ash, or milk in the fridge going sour and becoming yogurt. These changes can seem almost magical, right? Or maybe just random, but they're not. Not even close. They're all following a super strict, totally predictable set of rules. And the name of that rulebook? Well, that's chemistry.
So let's start right there with the big question. What exactly is chemistry? What are we really talking about when we say it's the science of transformation?
Well, the truth is, it's happening constantly, all around us, every single second. When milk sours and turns into curd, that's a chemical process. An iron nail you leave outside, the rust that forms is pure chemistry in action. Even something like making vinegar from sugarcane juice is a perfect example of a chemical transformation. These are not random accidents, they're predictable results that follow very specific rules.
You know, I absolutely love this definition from the Nobel laureate Roald Hoffmann. He says, chemistry is the science of molecules and their transformations. He just nails it, you know? It's not really about the 100 or so elements on the periodic table. It's about the infinite number of things you can build from them. Think about it like having a few dozen types of Lego bricks. With just those basic pieces, you can build entire cities, spaceships, anything you can imagine. That's what chemistry is.
And those Lego bricks, in our world, they're atoms and molecules. They're the fundamental building blocks of, well, everything. So when a chemical reaction happens, it's really nothing more than taking a structure apart and snapping those very same bricks back together in a new and different way. Just look at this. On the left, you've got a water molecule, H2O. 2 hydrogens, 1 oxygen. Simple enough. But on the right, you have carbon dioxide, CO2. 1 carbon, 2 oxygens. By just rearranging a few of the same types of atoms, you get 2 substances that are completely, totally different. One of them puts out fires, and the other one is made by fire. That's the mind-blowing power of just rearranging the pieces.
But here's the thing. This rearranging isn't just chaos. There are rules. In fact, there is one golden rule that governs every single chemical reaction in the universe. And that brings us to the laws of combination. And this is the big one. This is the cornerstone. It was figured out by Antoine Lavoisier way back in 1789, and the law of conservation of mass is actually pretty simple, but it's incredibly profound. It just says, matter can neither be created nor destroyed. In other words, whatever stuff you start with, you have to end with that same amount of stuff. The pieces can be rearranged, sure, but nothing ever just vanishes into thin air. Think about it like this. Chemistry is basically a game of perfect accounting. The universe is the most meticulous bookkeeper you've ever met. Every single atom that goes into a reaction has to come out on the other side. They might have new partners, they might be part of a whole new substance, but every last one of them has to be accounted for. No atom gets left behind.
And this idea of order runs deep. I mean, check this out. Look at the different ways nitrogen and oxygen can combine. They make totally different things, but notice how they always do it in these clean, fixed ratios. We don't have to dive into all the math here, but it's just more proof that chemistry isn't guesswork. It's a precise, predictable system built on these unbreakable rules.
All right, time for the main event. We're going to take that golden rule, the law of conservation of mass, and use it to solve a classic chemical puzzle. It's time for balancing the equation. So here's our puzzle. It's the combustion of propane, the gas in a BBQ grill. This equation shows propane reacting with oxygen to make carbon dioxide and water. But there's a huge problem here. As it's written, this equation is basically illegal. It's breaking the law of conservation of mass. The number of atoms on the left side doesn't match the number of atoms on the right. It's unbalanced, and we've got to fix it. And we're not just going to guess. We're going to solve this thing methodically. Here is our exact plan of attack. First, we'll check that the formulas are written correctly, which they are. Then we're going to go through the atoms one by one. First carbon, then hydrogen, and finally oxygen. And at the very end, we'll do a final check to make sure our accounting is absolutely perfect. Okay, first up, carbon. If you look at the left side, the propane molecule, that's C3H8, has 3 carbon atoms. So, to make things right, we need to have 3 carbon atoms on the right side too. Simple enough. We just put a big 3 in front of the CO2. Boom! Now we have 3 molecules of carbon dioxide. The carbons are balanced.
All right, next on the list is hydrogen. Back on the left, our propane has 8 hydrogen atoms. On the right side, each water molecule, H2O, only has 2. So how do we get 8? Well, we need 4 water molecules, because 4 times 2 is 8. So we'll just put a 4 in front of the H2O, and just like that, the hydrogens are balanced.
Okay, last piece of the puzzle, oxygen. Now for this one, we have to look at the right side first to see what our total is. In our 3 carbon dioxide molecules, we have 3 times 2, which is 6 oxygen atoms. And in our 4 water molecules, we have 4 times 1, which is 4 more. So 6 plus 4 gives us a grand total of 10 oxygen atoms on the right. To get 10 on the left, where they come in pairs as O2, we need 5 of those pairs. So a 5 goes right in front of the O2.
And there you have it. The puzzle is solved. This is a perfectly balanced equation. And what it tells us is the exact recipe. For every 1 molecule of propane you burn, you need 5 molecules of oxygen. And when you do that, you will get exactly 3 molecules of carbon dioxide and 4 molecules of water. Perfect. Beautiful balance. Let's just do that final check to be absolutely sure. This table lays it all out. On the left side, the reactants. 3 carbon, 8 hydrogen, 10 oxygen. And on the right side, the products. 3 carbon, 8 hydrogen, 10 oxygen. It's a perfect match. The law of conservation of mass is satisfied. So you might be wondering, okay, that was a cool little logic puzzle, but why do we do all that? And that brings us to the most important part of all, the chemist's blueprint, and why this really matters. Because what we just did, that wasn't just some abstract math problem. A balanced equation is a chemist's blueprint. It is a precise recipe for the universe. It's what tells you exactly how much rocket fuel you need to generate enough thrust to leave Earth, or the exact amount of ingredients you need to make a life-saving medicine without creating dangerous side products. It is, quite literally, how we control the molecular world. Which leaves us with a pretty fascinating final thought. You know, the ancient alchemists, they dreamed of turning lead into gold. And we now know that chemistry is really just the science of rearranging atoms. So if all we're doing is shuffling the same old atomic building blocks around, what are the true limits of transformation? What's really possible? It's something to think about. Thanks for joining me for this explainer.